All right. So I'm here to remind you of how to utilize conservation of energy to solve energy problems. What a lovely sound that always is. The situation I'm going to set up is one that's familiar. Our kid on a sled sort of problem. So we've got our sled up here, sitting on the sled. Whatever. There's your little reins. Great. Okay. So in my setup, they're up on a hill. We'll say that it's 6 meters high. And I'm going to give kid on a sled an initial velocity of, say, I don't know, 2 meters per second, let's say, up here at the top. 2 meters per second is our initial velocity. The problem will give you a mass. Well, generally, if you give them, you're given a mass or not, sometimes you need it, sometimes you don't. Masses will cancel out if you don't have friction forces, so don't be afraid if you're not given a mass and you're not given friction, but you will need it for friction. I'm going to give it one here because I'm going to work it both ways. So let's say that we have a mass of 60 kilograms. And what we're probably looking for, given this information, is probably the speed down here at the bottom of the hill, right? So our final velocity, that's initial, obviously. Our final velocity is what we're looking for here. So in the first case, I'm going to solve it without friction. Say that the problem says that we're considering it to be frictionless, and we're looking for final velocity. Well, this is pretty clearly an energy problem, or at least it's easiest to solve it that way. So with all energy problem starts, we start off with conservation of energy. Conservation of energy says that energy is neither created nor destroyed, only transferred. So that means that our initial, remember I used total energy, we just called it capital U. So initial total energy is equal to final total energy. Energy is neither created nor destroyed, it's the same at the beginning as it is at the end. So then you just set up what kinds of energies you had at the beginning and what kinds of energies you have at the end, right? So initially, we're up on top of this hill and we're moving, right? So we have both gravitational potential energy and kinetic energy, right? We have both PEG, P-E-G, gravitational potential energy, and we have kinetic energy, right? That's what we have at the beginning up here at the top. There's no elastic energy, right? There's no stretched spring or rubber band or anything, just these two. So that's all we have initially. And final, we're looking for, the final velocity down here at the end, right? We're back down here on the ground, so we don't have any more gravitational potential energy. We only have kinetic energy. I think now is a good time to remind you that you have the power to define where zero kinetic energy is, right? In our case, it's easiest to define, it's easy to define it as the ground here at the bottom right, where we have zero height, where we would have zero potential energy. But remember, that's arbitrary. You can define it anywhere. Remember, if we're doing an experiment on a table, you can call the table zero. It's not necessarily the floor zero. So be sure to take advantage of that whenever you can. So this is our setup, right? At the beginning, we have potential energy and kinetic energy. At the end, we just have kinetic energy down here at the bottom. The speed of this one, right? So now we can plug in potential energy, gravitational potential energy is mgh, kinetic energy is 1/2 mv squared, all on formula sheets, right? This is initial velocity. All right, so we can plug in our values here. Notice, like I said, whenever friction isn't involved, you could actually, the masses cancel out. So we can skip plugging those in, but then we just plug in, we have G, we have H, our initial height, right, is that 6 meters, we have initial velocity, and then all we're left with is final velocity, which is what we're looking for, so we can solve this. G is 9.8 meters per second squared. The test will probably have you use 10 anywhere that you calculate, if you even use anything to calculate it, so sad face, you can use 10, I guess. 6 meters for our height, 1/2, initial velocity is 2 meters per second, squared is equal to 1/2 final velocity squared, right? And then we're ready to calculate just algebra from here, which I will bust out the calculator for that because I did not do this ahead of time. 9.8 times 6 plus 0.5 times 4 is equal to 0.5x squared. Man, the cough. Alright, so what I got is that we have a final velocity at the bottom of 11.03, so basically 11.0 meters per second. Lovely. 11 meters per second down here at the bottom. Makes sense. We picked up speed, right? We had some of our potential energy get converted into kinetic energy, so it makes sense we're going faster. Plus, we go downhill, right? When we go downhill, we speed up. That makes sense. All right. So that is without friction. Now, I wanted to show you basically the same problem, but worked with friction this time, just so you could see both ways and how we plug in and account for friction in this case. Let me make sure I'm not going to screw up this calculation by giving us a good number. Okay. All right. So let's say that the problem tells you. Now we know how to. We can calculate friction as a value for work. Work equals force times distance, right? So you could get the friction force, multiply by the distance that the friction force is applied over, and calculate work. But problems are, especially FRQ problems, are much more likely just to give you a value for the work done in joules and not make you calculate things, because that's just like an extra unnecessary step. So it might tell you that friction removes, let's say, 1,500 joules of energy. So the work done by friction is 1,500 joules of energy, right? Because friction's doing work. It's adding or removing energy from the system. In our case, it's removing energy, right? So what if it told you that? What if it said we had friction? I'll erase this work right here. However, I won't erase the top line because it's the same, right? Effectively, our energy at the beginning should equal our energy at the end, but there's a small difference here, right? So our total energy, there's two places you can account for the friction loss here. You can either say, I think this is the easiest way, so this is the way I'm going to write it. So our initial energy is equal to our final energy, but only after we lose that energy due to friction, right? We started off with this much energy, we lost some due to friction, and now we have this much energy overall, total. Ooh, I guess. But yeah, so this is the setup for this, right? We had some initial energy, we lost some energy along the way, and then we had this much energy at the end, and we can plug in for that. So initially, same setup right here, right? We have potential energy initially, gravitational potentials to be specific, and we have kinetic energy. So we have PEG, we have kinetic energy, and then we lose some due to friction, right? Friction does negative work, negative sign here, right? Because friction's removing energy from the system. And at the end, we're only accounting for kinetic energy. So, PEG mgh plus 1/2 mv squared minus the work done by friction plus 1/2 m, that's a v, mv squared. Except this initial velocity right there, right? That's an ugly, ugly looking thing. All right, so we're ready to plug in. Notice you can't cancel out masses here, right? Because this term doesn't have an m with it. If you feel like you're going to screw that up with the algebra, just never cancel the masses out and be safe. But in this case, masses do not cancel out because this does not have an m. So we plug. Mass is 60 kilograms. G is 9.8 meters per second squared. Our initial height is 6 meters plus 1/2 times the mass, which is 60 kilograms, times, remembering why some of us didn't like these problems because there's lots of numbers to be writing, minus our work done by friction, which is that given value of 1,500 joules. Yay, two-line equation. 1/2 60 kilograms times our final velocity, which is what we're looking for, squared. So all we're missing is final velocity, which means we can solve for this value here. Allow me to calculate. Same setup, just adding in the account for friction. No, I don't want to do cosine. Minus 1,500. Alright, so I got that we have a final velocity of 8.46, so 8.5 basically meters per second. Boom. slower than our 11 meters per second, right, which was our frictionless case. So that checks out. That makes sense, right? We're going slower because we accounted for friction. Easy peasy, right? Conservation of energy, not very complicated. And this is how you solve and how you can solve any and all energy problems. It's just this basic setup right here will do you just fine on any problem that you're thrown at. The only thing that you have to remember, and you don't even have to remember because it's on the formula sheet, is your formulas for which types of energy, and being able to identify the types of energy, I guess. But we can handle that. That's like 8th grade stuff. All right, so that's how you do conservation of energy. Pretty straightforward. Good luck on the practice problems.